So today we are very honored to host Professor Matthias Scheffler visiting the School of Physics, Peking University. Matthias was my PhD supervisor. To me, he's my PhD supervisor. To me, I think he's a man with wisdom and a scientist who is very far-sighted. I will convince you with this point by 3 stories I've experienced in my education. The first one is when I was a PhD student. I asked Matthias, why do you choose density functional theory as your research area? And he told me in the mid of the 1980s, he saw a paper on PRL comparing the enthalpy of graphite and diamond, where the stability of graphite compared with diamond is very accurately demonstrated by local density approximation. And then he belongs to the first group of people who concentrate on the application and development of density functional theory and use it to study the real materials. So the second one is when I was doing my PhD, I clearly remember, and I mentioned this to Matthias on the car. In the year 2005 or 2006, he came to China visiting the Institute of Physics and the Institute of Chemical Physics of the Chinese Academy of Sciences. Then after he came back to Berlin, when we finished one group meeting, he asked all Chinese people in his group to stay for a while. And then he told us that I see huge improvement of scientific research in China. The Institute of Physics has done fantastic research to him, he think. And he suggested us to think about coming back to China for our academic career, and I took that suggestion very seriously. And actually, I planned my academic career according to that suggestion. After finishing one postdoc with Angular's microlides in London, I came back to Peking University, and I think I benefit from this suggestion. So the third one is related to the topic today. You know, the Nobel Prize was awarded to AI this year, but I have to say, Matthias belongs to the first group of people who has seen this future, like not more than roughly 25 years ago. So he started his first work on neural network in the year of 1999. It's basically last century. And his first publication on this was in the year of 2004. Far before we realized the importance of this technique. In Germany, I think to judge the taste of a scientist, we often use the word, some negative word like someone is trendy. But I think Matthias is just the opposite of it. He belongs to the person who can see the future of a certain field and to influence that field. Yeah. According to the academic contribution of Matthias, in last year, when we celebrate his 17 years birthday, I try to summarize it into 3 aspects. The first is the development of first principles method and really the pioneering people who use it to study the realistic materials. And the second aspect is to thinking about simulating very complicated chemical reaction scenes using technique like kinetic Monte Carlo and make people understand what is happening on the very complicated surface in the atomic level. And the third part is, of course, this development of the machine learning method, which has, I would say, make a big impact. Huge impact on our field. He has received many awards. I don't want to list the papers he has published because the number and as well as the citation is astonishing. Just to mention that he, besides this, he was also awarded some very important medals in his career, like the Max Planck Research Medal, the Max Born Medal, as well as the Ernst Mach Medal. I think I shouldn't waste too much time, and I will give the phone to Matthias, and let's welcome him. Thank you.
Yeah, thank you very much for these very nice words. So I'm not sure if I can predict or know about the future, but I think what I'm doing is usually I'm really listening very careful to people. Yeah, good ideas which I like. Then we do this, and there's also a lot of luck that the ideas which you test that they really finally work. And of course, yeah, it's luck and as you all know, a lot of work. And I'm privileged actually that I have been so early since 1990 really connected to China, and that I've seen this enormous changes in sciences. And I mean, the last conferences I have been here, not only from the quality of science, but also from the way you discuss things. I think actually, I mean, in the past, my role model was to some extent the USA, but actually now in science, I would say actually with what the equipment which you have and the way you are doing science, you are at least equal to them, and if you go on, you will be better, right? And and this is just great to see these big changes and the success. So thank you very much, Xinjiang, for this nice introduction. It's really great to be again here at Peking University. I was here 2015, and that was in fact in the chemistry when Jian Hong invited me to what was called the Jingda lecture. Now I'm a physicist by training, so actually it's actually even nicer to be now in the physics school. So this lecture will be, as you have heard, about artificial intelligence in material science. And I will address the impact what artificial intelligence has. But I also like really to stress uncertainties and uncertain expectations that people have, and of course open challenges where we see what may happen and what is needed, in fact, what is new and exciting coming, and where we need also new ideas in the basic concepts of these methods. The same question which I will discuss for material science, I really believe also exist in other fields, but they're typically not mentioned. And I think actually it's very important to really be careful in when you use methods, and that you know what are the limits. So what we are seeing at the moment, since quite some time, is that we are in the middle of what I call a transformative shift of how materials research is being performed. This is also called the fourth research paradigm in material science. And let me just say a more general word. The term new paradigm does not really mean this is a new method. It is a new way of thinking, and I will explain this in a moment. The key issue concerns that we are now using AI, talk more about correlations, which is really different to the classical scientific approach of material science, which is aiming at causation. I will discuss later in detail what this means by using some specific examples. And I will also show you some AI methods which bring some of the causation back, not really the full as we had it in the past. And this is the new way of thinking, and you will see this hopefully better later. And this brings me to the concept of what we call materials genes. Materials genes are basic materials features or basic materials characteristics that play a similar role as genes in in biology or medicine. So such features for material science could be local structures, that is the position of the atoms in a solid, or it could be certain quantum mechanical properties of the atoms that build the solid. So like the S, P, and D wave functions of the free atom. So these are basic features which somewhat characterize the solid, but they somehow determine the properties. And so for example, a property which you're interested in may be the band gap of a semiconductor, because the band gap of a semiconductor determines if this is a good material for photovoltaics, and just to name one specific examples. However, what is not known for the genes in biology, and not really for the genes which I'm talking about, is the full scientific relationship between the genes and the property of interest. You will see that there is a correlation, there is some connection, but the scientific relationship is typically not known, and I argue typically in realistic situations it cannot be expressed in terms of a meaningful equation. Therefore, the relationship between materials, genes, and the property of interest is not described in terms of scientific laws, and this relationship is not derived from scientific laws, but it is described in what we call, therefore, rules. And this means that we don't deal with clear, okay, thank you. Actually, I have two here already. Yes, thank you. That means we don't deal with clear predictions. Instead, correlations are described by statistics. Thus, we predict probabilities and probability distributions. Thus, we predict a mean value, and we predict, in principle, an uncertainty or a variance of the prediction. This is often forgotten, and maybe actually even on purpose or not really told, but this not really telling about that there is an uncertainty for your prediction, that this is a statistical method, is, I think, one of the big risks when people use artificial intelligence. And this is, again, the reason why I'm using the concept of genes. In biology, as you know, a certain number of genes, I think say 10 certain genes, tell that you have a 70% chance of this type of cancer. Or 100 genes tell actually what is your hair color when you are younger than I, then at some point that is no longer determined by genes. But it tells it actually with a certain probability, right? I mean, it's a probability of 70% getting this cancer, and some people take then some protection, but there's never really 100% prediction. And the analog is true for materials genes. A certain combination of certain materials genes tells a certain probability about the property or the function of the material. For example, it predicts, we have one example, that there is a 90% probability that a certain group of atoms, if you create a crystal out of these atoms, will become a stable perovskite. And such a prediction, which we did actually with machine learning, was actually one of the most successful things we have done, because perovskites, I show them later a little bit, are very important materials in technology nowadays. So this is what we can do. We give predictions with uncertainties. And this is what I mean with a new way of thinking. We're looking at correlations. You can say we are largely ignoring the laws of physics and physical education, but we are looking for correlations instead. Now, of course, that's not good to say so in a university, but you can say this also in a more positive way. We like to say that we acknowledge that there is a higher complexity in the world than what can be expressed by classical mathematics or by partial differential equations. We have actually possibilities in mathematics, but the intricacy of many processes which may play together in some statistical way may be actually much more complicated for realistic systems. You very often may actually be able to isolate some systems, and then you can do things in a very understandable and explainable way. But in realistic situations, as I will show you later, we believe this is not possible, and therefore one should acknowledge that the intricacy is high and that we just can give probabilities, as in medicine and biology people have decided to go to the genes and correlations. So having discussed the fourth paradigm of material science, let me just briefly mention the first three paradigms, just to have this a complete picture. The first paradigm in material science is the experimental or empirical research. This is the initial one. It started back in the Stone Age, or maybe when the Stone Age changed to the Copper and Bronze Age. Back then, the first metallurgical techniques were developed. The control of fire was really the reason for the breakthrough, that you could really create from stone and from minerals metals. This paradigm, or this way of doing science, is of course still valid. I mean, a new paradigm does not necessarily mean that you replace the old paradigms. It actually, in my understanding, it really gives a complementary and additional way of thinking. Then in the late 1600s came the second paradigm, and this change was led by Galilei, by Kepler, and by Newton. And Newton and Leibniz, they developed, in fact, the differential, and since the end of the 1600s, differential equation became the tool for describing scientific laws. And not only scientific laws, but actually in physics, also in chemistry, and actually also processes in engineering. Paradigm number three started in the 1950s, I would say to some extent with work by John Slater, and then Walter Cohn and others. This was and when the Monte Carlo method and when molecular dynamics were developed. All these methods enabled, also because computers became now available, enabled computer simulation, computer-based studies, which somehow mimicked what you could see in a clean, well-defined experiment. And since then, people did computations more and more in a similar way as people are doing experiments. And then these computations, the results were also analyzed in a very similar way as experiments were analyzed. The fourth paradigm is what we discussed already, and here it's called data-centric science. And this is what I will discuss a little bit in my talk. Now, if one likes to employ AI, or if one likes to use data-centric science, it's obvious you need data. Therefore, we started about 10 years ago to build an infrastructure that enabled a fair data sharing. And I will come back to this in a moment. I want to have some historic remark first. And this is a historic remark which shows a situation which is still true today and which is hampering the progress of science. The critical role of data collection and sharing has been known in science since a very early time. And one example is the tense relationship between Tycho Brahe and Johannes Kepler. The former, that is Brahe, you see also when they lived here, he had the best data in astrophysics at that time. But he guarded them carefully. He wanted to do the interpretation by himself. He did not share. Kepler was probably the best mathematician of that time. He was very interested in Brahe's data, but he didn't get them. Only later in his life, Brahe decided to invite Kepler to become his assistant. The untimely death of Brahe, just 1 year after Kepler arrived, gave Kepler the possibility to get all the data. Now, there was an accusation that Kepler may have killed Brahe to get the data. That was checked, but actually was probably not true. But the relatives brought the case to court and said actually Kepler has stolen the data. Nevertheless, based on the data, Kepler developed what is now known as the law of planetary motion, the Kepler laws. And despite their tense relationship, they are honored here together. Brahe for the measurements and Kepler for the interpretation. Each of them alone would not have achieved what they have achieved together. Although actually together is in quotes because they never worked together, right? I mean, the Kepler laws with stolen data have been then very important. I mean, for really the development of physics, they were really also essential for Isaac Newton for develop the theory of gravitation. So the concept to convert information about nature from data into laws of nature and into analytic equations, this is typically related to the work of these people that are listed here. Together, actually, maybe with Gottfried Wilhelm Leibniz, because he was influential also in developing the differential. So the Brahe and Kepler example concerns astrophysics, but it's a typical thing in really not sharing, but trying to do things yourself. But I think if there are other people, why not really do it together? And I think one should not wait that somebody kills you. Give the data and do good work together. Now, as many people from different fields, not only material science, I have one slide on material science. Why is this an interesting and important area? This field plays a pivotal role in fostering, I would say, the prosperity and enhancing also the lifestyle which we all have. I mean, nearly all the things which we have in our hands are really related to material science. It's also actually a science which is really crucial for development of environmental and sustainable technologies. The field of material science is profoundly interdisciplinary, encompassing physics, chemistry, biology, mathematics, and computer science. And basically all products which are critical for sectors like energy, environment, health, mobility, information technology, rely on new or even novel materials which we didn't know that they even exist some years ago. Examples are touchscreen on our phones, solid-state lighting, solar cells, batteries, also implants in medicine like artificial hips and teeth are now actually very much affected by material science, and drug delivery and many more. Obviously, as I said before, if you want to do data sharing, or actually if you want to do data-centric science, you need data. And therefore, we started about 10 years ago to build what we call the NOMAD database, or NOMAD data infrastructure. The basic concept is described in this Nature paper, which you see here on the right top. For the NOMAD research data infrastructure, we invited everyone in the field of computational material science to upload their data to our repository. And we felt that this uploading has to be as easy as possible. If it would not be easy, people would not really do this. And so we did not really request a certain format. We told people, upload the data in the way your computer code is creating them. And but the important thing is we said, we don't want just the results. We want the full input and the full output file. So that if someone wants to repeat these calculations, or if someone wants to really know actually how accurate, how reliable is that, the person can really test that. And so that was surprisingly successful, as you see it here. So there is this repository. Now this repository maybe not useful for many people because, as I said, these are the data, the way the computer code gives these data. And there are 50 different computer codes which all have a somewhat different formats. But what then we have done, and of course if you have computers, this is what you should do. We are processing the data. So we are parsing them, we are renormalizing them and bringing them in a standard format. So people do not have any work, we do the work. And then in the archive, we have data which have the same format, and these data can be now used by anyone who wants to use them. We see now that there are many millions of data and actually billions of results in this archive. And these two things together, the repository and the archive, they are what is called fair. That means data are findable, they are accessible, they are interoperable. You can use them also for other things than what the people had in mind when they created them, and they are reusable. The important thing is that when people upload the data, these people should identify themselves. They also get a DOI so that these data are citable. When people want to look at the data or they want to download the data, they do not need to identify themselves. They just implicitly accept this so-called CC BY license, which suggests that you should cite the person who has created the data. So this is now the biggest data store in the world. And I mentioned that NOMAD is fair in the standard definition. Now my motivation was slightly different in fair. I wanted that the data are findable and AI ready so that you now actually have them all in the nice format and you can use them for a next step. One reason that we have so many data is that we have friends in the USA. In particular, there is the AFlow lib by Stefano Cottarolo. There's OQMD by Chris Wolferton, and there's the Materials Project by Christine Persson and Gerd Seder. These are good friends of mine, and we have all their data also in our database. So about 50% of our database is in fact their data. I mean, they are more narrow. They only have actually one computer code. They only have more or less data which they created themselves. In our case, there are hundreds of different people who upload their data. It's really a more community effort. Now we started from computational science because this is my field and this is where I have most of my friends. But we then felt that we have to continue and we should go really also invite people from the experimental world. Now this, and we are now in fact adding data from synthesis or crystal growth and from experiments. This is much more complicated. I mean, in computations, we know what we are doing, right? When we have an input file and we have an output file. In experiment, to really characterize the sample which has been studied in all details and really give all the parameters which are really relevant for doing a measurement is still not 100% developed. So people are now, this is called metadata. Metadata describe basically what the sample is, the sample history, because as piece of material changes when it's actually getting older or when the sun is shining or whatever. Having all this information, people are now working on it. This is still something in progress, but it's actually going on because people also in experimental science, of course, see how important it is to have, I mean, in principle, I would say, this is how science has to be. Science has to be reproducible, and you have to give all the data. But in material science, in crystal growth, this is very, very difficult. And that's why it's more an art to grow a crystal than really 100% science, because a lot of things these people who do this know what to do, but they have not really documented all the details. And they even maybe not know this in detail, but they have this in their feeling. But NOMAD does not stop here. So there is what we call an encyclopedia, getting the data so that you can also look at it and say, I want a specific heat, or I want really this and this. So there is some encyclopedia to really analyze the data or present analyzed data. And there is what I was mostly interested in, this so-called NOMAD Artificial Intelligence Toolkit. This toolkit, these are Jupyter notebooks, which often go together with a publication. I mean, this is also something which you realize when you read the literature. A lot of publications just say, actually, we use machine learning. Maybe they still say, actually, we use random forest or so, but they don't give any detail what they really have done. And so having a Jupyter notebook connected to that, which really describes the details of the machine learning, is very important. And it has the advantage that people can use these notebooks. They can change the parameters to see what would happen if the parameters would be different, or you could change some of the logic in the notebook to really adjust it to your own different research needs. So this is what we have done, and which I think is actually very important, and I know that this is also happening now somewhat in China. At least I met several people now recently who try to do something very similar. But the point is really one has to convince people to share, and that everybody also realizes creating good data and describing good data is a lot of work, right? I mean, typically we think actually we want to publish, but doing everything careful is a lot of work. And I think in the future, also when we evaluate people, we will actually also evaluate actually how careful have they been with their work and presenting what they have really done. So let me come to the big chance such repositories or such data are, but also to the daunting challenge for material science and engineering. The number of possible materials is practically infinite. And that already tells that from all the materials which we are using, be it a light or be it a touch screen or be it even a tool which you use for even a steel or whatever, or to build a car or something, there are most likely materials out there which are better than what we are using today. But of course, how can you find them? If it's an infinite space, how can you find the best material for a better touch screen? So as the number of materials is practically infinite, there is no way to cover this space by just doing calculations or measurements, right? I mean, even if you do 10,000 of calculations or 10,000 of experiments, this is still nothing compared to infinity. So there's no way to really scan over this whole space by high throughput screening experience or by high throughput computations. Still, these high throughput studies are very important because they give us data, but they most likely will miss the relevant data. The daunting challenge is what I said before, that the interesting data are rare. Right? You have infinite number of data, but how to find the very few which are really relevant? The interesting materials are statistically exceptional. So if you have a system, if you look for a better catalyst for a certain chemical reaction, there is practically infinite number of materials, but maybe just a handful of materials which is good for this type of process you're interested in. So how to find this? Our approach is to create what we call maps of materials properties using artificial intelligence methods and concepts. And here is such a map where we have an x-axis which is called descriptor D1 and a y-axis which is called descriptor D2. Initially, we do not know these descriptors, but we say if we would know these descriptors, D1 and D2, we are convinced that in this XY plot, there will be regions where you find materials which are good thermal insulators, or there will be regions which are good for heterogeneous catalysis. And then if you have identified these regions, you go there and then you dig in only there, not everywhere else anymore. Now, of course, you need these descriptors and to create such a map. This here is actually a two-dimensional map. In general, actually, the map can be much higher dimensional. It can be 3, 4, 5 dimensions. You will see, which we were really surprised. Very often it is two-dimensional, or two-dimensional is good enough. But in fact, in principle, also, when I say here, this is the region where you find good materials for photovoltaics. I mean, regions may overlap, but in fact, there's also no reason that it's just one cloudy shape. It could be also actually several islands in addition. We don't know that, but this is what we would like to do. To really find better materials, we think we have to create maps which tell us where we should really search, so that we're not really searching everywhere where maybe it doesn't make sense to look for. So we are working on all these topics which are listed here and even on more. And as indicated before, high throughput screening, and also what is now coming, which is also very important, these automatic, these robotic labs where people do experiments by robots, which has actually the advantage that now you really determine more carefully all the details in the experiment, are very, very important. But what we find when we look at our database is that this traditional way of high throughput screening creates a number of redundant data. If you look at the database which we have, 90% or more of the data can be removed without changing the information content or without impacting the performance of an applied machine learning model. So if you just choose materials randomly, you choose many systems which are very similar to what you have calculated before. And so we do a lot of unnecessary work. 90% seems to be unnecessary, but of course we didn't know before that. And so what we are also saying is, and what I will also go into this a little bit more, it's better to intelligently select which materials should be studied next. Just to make a clever choice and not doing too much redundant or unnecessary studies. This has been also, in fact, published by Kangming Lee and others and discussed in this paper very nicely. Thus, a subjective or random selection, we think, is not really a good idea. Choosing systems intelligently, but how can we do this? So let me discuss this and the associated challenges a little bit more. And this is some work we did with Lukas Fopper and Mario Bolley in Berlin. The idea is you start, of course, with a data set. So the x coordinate somewhat, it's most likely a vector, is our features. The x defines what the material is or the temperature is and so on. And the y shows actually this material has, for example, a certain band gap. Y could be a band gap, or Y could be a catalytic performance and so on. So you start with these data points, calculated or measured. Then with these data points, one does a machine learning model. But in principle, there is a true function which nobody knows. But we know this only when we have, say, 3 or 4 data points at 3 points. So these are the points which we know. But we want to go to the best ones. So we then, in fact, continue. So we use our first machine learning model, which could be the blue curve that you see here. We analyze that, and from this blue curve, we look where is the next data point which would carry the most new information. And this data point is then calculated or measured and added to the data set. Then we have a better data set. We do another machine learning model, which is here. This machine learning model gives us another suggestion for a next point and so on. Now the problem in machine learning is that machine learning assesses, so a machine learning model assesses the description in average. Now, we are not really interested in a model which gives a description of the average of the infinite number of materials. We are interested in a model which tells us which are the exceptional materials. So good average performance might not translate into a good description of statistically exceptional materials. So again, we need to think how to do the next choice of a new material. And I give you one example. We started with a more tutorial example, and I then show you some specific application. So we use two machine learning models. There are two ones which are really some more or less classical. One is called Gaussian process regression and the other is called random forest. The reason of that is that these two methods, in contrast to the more modern ones, these two older methods have the advantage that they not only give the mean value, they also give an uncertainty. And then we combine these two machine learning models with two strategies that are called acquisition strategies. That means strategies which tell us what is the next point we should add to our database. And one of these strategies of acquisition of the next point is called pure exploitation. Pure exploitation just means you trust your machine learning model and you only look where your machine learning model gives you a good value. And you just really only look at the mean value of the machine learning. And then the other one is expected improvement. That looks more at the uncertainty. That tells here is something uncertain. There I should add another point to really improve on the quantity, on the value which I'm interested in. And so this is how it looks. So we have, as I said before, there's always what we call a ground truth. But this is something as a function of, say, materials. So the x-axis would be materials, and this is here the property, let's say, a band gap as a function of material shown here. The ground truth is not known. The ground truth is only known at the measured or calculated data, the black points here. And machine learning gives you the gray, so very different to the truth. But machine learning also gives you that every gray has really a width, and that is the uncertainty of the prediction. And then from the mean value and the width, we have this acquisition function. This is the green one, which is just a function of the mean value and the width to some extent. And that tells us the next point, maybe actually you should calculate this one. Now, in principle, you are interested in the best performance, so you would like to find this point here, but in this case, you find, in fact, it goes in the wrong direction, but of course, no one knows that. This is at least what the acquisition function tells you. Let's add this point. You add this point, you do a new machine learning thing, you get a new acquisition function, but the next acquisition function tells you, you went in the wrong direction. Now, actually, you should really maybe try this point. And then the next one says this point, this point, this point. And so after 5 iterations in this simple tutorial example, after 5 iterations, we have found the maximum. So we are not doing a random search, we are really doing a search which is guided by the knowledge of the mean value and the uncertainty, and we find the maximum very fast. This also means our machine learning model is not improving in average. We are only improving in the region where we really see the performance is good. And let me show you this now for one specific example from the real world, if you want. And this is for so-called perovskites. Perovskites is an important material that has actually applications in the next generation of solar cells, but in fact also in catalysis and many other properties. It's a very interesting mineral which has been found about 200 years ago in Ural in Russia, and it's named after, it's not really named after the person who found them first, but after Mr. Perovskite, who was a Russian, he was a mineralogist, but he was also the Minister of Internal Affairs at this point. And these are materials which have an interesting, very, to some extent simple, but also not so simple structure. You have one metal, so A and B are metal atoms and O is oxygen. So one metal atom, let's say the B atom, is sitting in the middle of these octahedra which you see here. So there are metal atoms which are surrounded by 6 oxygen atoms, which form an octahedra. And then you have 4 octahedra which surround the other metal atom. And you can say these so-called simple perovskites, or you can make them actually double by really having 2 different bees that would be just twice longer in the X and Y direction, in that direction. So we were asking which of these, if you really look for perovskites, and there's basically an infinite number of perovskites which is possible in just changing these atoms the way I described it, how can we find the perovskite which has the highest bulk modulus? Bulk modulus, for the non-material scientist, is somewhat telling you how stiff a material is. How much energy do you need to compress a material? Can also say related to hardness or something. And we want a perovskite which has a very high bulk modulus, which you cannot really, which will not compress very much if you put a lot of force on it. And so we start with something like 800 data points for these perovskites, which I just mentioned. And we did 2 machine learning models, Gaussian process and random forest. And you see, and the full line is really the training. So both methods, both machine learning methods are essentially giving the same quality, the same error bar. It goes down really very low, to small numbers if you have 800 data points. So usually in machine learning, you have your training, but then you use this machine learning models also for systems which were not part of the training set. And there the quality is of course slightly less. It should be not too much less. And this is also a good example here. So the prediction error is for the random forest, the blue curve, for the Gaussian process, the red curve. So the random forest is slightly better, but again, I mean, also in the prediction, these 2 methods are doing pretty well. And now we do this iterative tour that we say we add actually data points in a systematic way. So this is the maximum bulk modulus plotted on the y-axis. And this is the number of iterations. That means the number, for every iteration, we add 1 more data point to our data set. In the beginning, we started with 800 materials. The best bulk modulus, the best material had a bulk modulus of 1.4. If you would do it the old way and just adding in a random way more and more data points, you have a good chance to getting better. The uniform sampling means actually this random addition. And after 30 iterations, adding 30 more data points in a random way, you are slightly higher. If you do it the way I just have described it, you do your machine learning model, you make a prediction, you calculate an acquisition function. The acquisition function tells you what material you should add. The best example is the orange one. You see after 30 additional data points, we have increased our bulk modulus from 1.4 to 1.75 significantly, only after a few iterations. So you would not, I mean, doing this with a random sampling, that you reach this data point will be far, far away and in a much more inefficient way. But you also see that different combinations behave differently. So this is the expected improvement together with the Gaussian process. The pure exploitation, which does not really consider uncertainties, and the random forest is not so much worse. And the expected improvement with random forest is getting similar to this one. But it really depends. This is something we learned from that. It's still a research project. You don't know really for sure what is the best acquisition function you should use. And so there is some still basic research necessary. It's crucial to choose the proper combination of acquisition function and machine learning model to have, and that means it's important to have a reliable quantification of uncertainty. Now, let me now add a little bit more about uncertainties, because again, this is something where I'm sure in the next years there will be hopefully some breakthrough in understanding this better. The best example I felt I have for discussing uncertainties is some work we did with Ki-Sung Kang. He's from Korea. And this is on what is called machine-learned interatomic potentials. Now, material science is all about where the atoms are, how atoms vibrate, how they could change, and you usually calculate this with very expensive density functional theory calculations. With these, you can calculate you cannot calculate very big systems, or you cannot calculate very long time sequences, because if you want to see if an atom which vibrates maybe jumps here and moves on and so on, you can do a little bit, but not really all the things you like to do. And therefore, there is what is called machine-learned interatomic potentials. There is a way to describe these interactions by machine learning and use this model then for really longer timescales or for bigger systems. So machine-learned interatomic potentials start, of course, from ab initio data, because you need some data, but then for training, but then in fact they follow what this other community in biology mostly, or polymers, is doing, so-called force field concepts. It then really continues just with very fast machine-learned potentials. So you need quite some computer time to train your potential, but then you are fast in your machine-learned potentials. So they are fast after training, but the problem is they may produce incorrect results, because, as I said before, machine learning works for the points where you have trained it. If you are a little bit away from these points, you don't really know how good the model is. And similar to what I said before about exceptional materials, also in the dynamics, we have exceptional processes. We have so-called rare events. So an atom is usually vibrating, but once in a while it may actually move to a different thing. That doesn't happen very often. And rare events are really crucial for understanding phase transitions. A classical example is just cooling down water. I mean, if you cool down water slowly, you can cool it down and it's still liquid at minus 20 degrees centigrade, if there is no rare event. But then if you kick it a little bit, it will immediately freeze. So understanding rare events is really important, but if they are not really in the training set, the machine learning potential will not know about that. So the point is, the machine learning potential can only, and any machine learning can only as good as the training data is. There may be, these rare events may be missing in the training data. But I said before that a machine learning model works good in average. It does not really work good for exceptions. And so there is what is called regularization in machine learning, which is somewhat a type of smoothing to make a little bit this machine learning a predictable method for outside the training. So rare events may be smoothened away in the training process. And because, as I said, machine learning minimizes the overall, the average prediction error using regularization. Or, so they may be missed, but in fact, a machine learned potential can also have fake rare events. It could have an event which is not realistic, because it can have everything. It can do, and so also that you don't really know. So you never know when this model breaks down and if the results are really trustful. So how can we detect possible errors, and how can we improve on this? So the machine learned potential calculates the potential energy, the energy of all your atoms in your system, as a function of the atomic positions. And if the ground truth, so if you would do a DFT calculation, density functional theory calculation, would be this dashed line here, and you have only data here because this is where the atoms vibrate, and you use different machine learning potentials by, for example, different seeds, different initialization, or slightly different data sets. They will all agree in this region. But as soon as you go outside the region, they will actually show a different behavior. And if this rare event, this other minimum, was not included in the data set, they most likely will not find this rare event. To really have and that tells you already about the uncertainty. To have really a good description of uncertainty, you need something like 10 machine learned potentials which you run parallel to each other, and then you get actually a width of a distribution. And so it tells you that there is no uncertainty here, but then some uncertainty starts becoming important here. The picture is also, it's really a realistic picture. It's very important. It gives you an uncertainty, but you see the error is much, much bigger. So these uncertainty estimates do not really give you an idea about the error. They are overconfident. They seem to tell you it's much better than what it actually is. So uncertainty estimates is the variance of an ensemble, but they are very often overconfident. And I show you this here, how we are using it. So this is a case of copper iodide, which is a nice structure, usually as you see it here. But once in a while, one of these copper atoms moves up, and you have something like, so here was the copper atom was first here, so now it's a vacancy and an interstitial. So you change from a nicely periodic crystal to something which is a defect, a vacancy and interstitial pair. This was in fact this double minimum which you've seen before. So density function theory has this double minimum. If you start with the machine learning potential, you get the yellow curve, which has no clue that there is actually this interstitial pair forming. And you can calculate the uncertainty. You get actually a small number, 0.1 electron volt, and you see the error was much, much bigger. So what we are doing now is, as soon as we see a small uncertainty, we say, at this point, you need another data point. You should not trust the results. There is a small uncertainty. Just add another data point in to your machine learning training set and do a new machine learning model. And so the next thing after the first is the active learning process number 1. Then again, you see there's still uncertainty, active learning number 2. And at number 5, we already actually now have really found the full curve. The interesting thing is that the error and the uncertainty as a function of adding these points look very different. So the error is actually a step type of behavior, right? So after 3 iterations, we are much better in the error. The uncertainty is somewhat smooth and much smaller. And so again, uncertainty is giving you a flag. You have to be careful. It does not really give you any reliable estimates. Ensembles are overconfident. They do not correlate quantitatively with the true error, but still they are an important indicator. Uncertainties are naturally provided by Gaussian process and random forests, which I mentioned before. For all other methods, one needs, at the moment at least, ideas like ensembles. Now, ensembles, as we also have seen, are not reliable estimates, only an indicator. And you can do ensembles in very different ways, and we are testing the different ways at the moment. You can use different training data from the pool. One can use different starting conditions, because if you have a neural network, the way you start, what your initial data points are, gives you also slightly different neural network potentials. I will talk about CISO in the next 10 minutes. Do I have still 10 minutes? Okay. And another method in a moment where you see actually there are other possibilities where you could actually also do things in a different way. And you will see this actually on the next slide. So this is another specific example of how I think machine learning in our field should be used in the future. This is work by Tom Purcell, who is now professor in Arizona. It's a method which is called CISO, and I should say actually, and which deals with thermal insulators. Again, this is a very important class of materials. So these are materials which do not conduct heat. I mean, you may want that if you drink tea, that you don't burn your fingers when the hot tea is inside your cup. But actually also these materials are used in airplanes, in jets, to save fuel. Air jets are run at a temperature which is above melting of the metal. Now, if the metal would melt, then of course the thing cannot work anymore. So there is a very thin thermal barrier coating on the metal to prevent it from melting. And another thing is so-called thermoelectric materials. there are materials which transform heat into electricity. Most of the energy which we consume goes together with unwanted heat, which you also call waste heat. And this heat we usually give into the groundwater or actually into the air. But of course, it would be much better if we could recover this heat in terms of electricity. This works in principle, but we don't have a good material which makes this efficiently. So you want a good thermal insulator for making this happen. Now, thermal insulators are not fully understood because they are strongly anharmonic. And that means, again, you have the same potential energy surface which we had before, the energy as a function of atomic geometry. There is an equilibrium geometry, and typically people describe solids in a way that they say the atoms are sitting here and they just vibrate around this point. But as we have seen already, sometimes there is actually a defect formed, and it could be that you also jump to this other point. And if you would do a thermal conductivity calculation, starting from this point and just doing perturbation theory, which is called Boltzmann transport, you would get the thermal conductivity of this level, but the experiment is down here. And the reason is, in fact, there are other minima which are also visited very much. And these other minima are really important, and they are so different from the initial minima, you cannot really do a perturbation theory. Perturbation theory you can do if perturbations are small, but here it's really qualitatively different. And so we very strongly say that for many systems, particularly for anharmonic systems, the phonon picture is not really valid. You should really use the full dynamics of the nuclei. And you see this also if you would evaluate, I mean, all these quasi-particles in solids have a certain lifetime. And what you see in these systems, that the lifetime of a phonon, so a phonon is really some atoms are vibrating from the left to the right, but if the lifetime is short as one vibration, it doesn't make sense to talk about vibration anymore. And so this is somewhat where we see the limit. And so we have developed a method to really calculate everything correctly, and then we are getting at least very close to this. But the example I want to really show you is something which we do also with machine learning, and there a crucial point, a scientist was Runhai Ouyang, a Chinese person in our group some years ago, who now is professor at Shanghai University. So he basically developed this methods which we call sure independent screening and sparsifying operator. It's a combination of symbolic regression and compressed sensing. That means it's really a different method to what I said before. This is a method which tries to find the best analytic function, an analytic function which does not really tell the physics, but which correlates with the property you want to describe. And so you offer many analytic functions, and then from these many analytic functions we select the function which has the best correlation. And this selection is done by what in mathematics is called compressed sensing. And for the mathematicians, typically in compressed sensing, people do an L1 regularization. The best thing would be L0, which is typically too inefficient, but we found a way to do this. So we do, in fact, the compressed sensing, the selecting of the best correlation with the L0 renormalization. And so very fast, the method goes as follows. We select what we call primary features. So these are the properties, the individual aspects which describes the solid. So these are, say, again, maybe a geometry information. It could be just the SPD electrons of the individual atoms which create the solids. Anything which you believe could be relevant for the property you want to describe, for the catalysis or for the heat conductivity, all that should be offered. It's not really what is important at the end, but we should offer as much as possible. And then we combine these features by adding them, subtracting them, exponential, logarithm, again and again. And in this way, you create very fast 1 trillion of different functions, 1 trillion of functions of these initial primary features. And then from these functions, by compressed sensing, we select the one which is relevant. And we find typically that 1 or 2, maybe 3, are actually most important. And so we say this function which we find is just measuring or describing the correlation between the initial features, which I in the beginning also called genes, and the property of interest. The function is not really physically meaningful, but the parameters which enter the function must be related to the physics which is driving this thing. So here you see the result of the CISO model. So this is the thermal conductivity as a function of, so this is the prediction as a function of really the measured value. So in this case, we started with experimental data points. We had 75 experimental data points from the literature. We did a CISO analysis. I show you this in the next slide. And we get a very good correlation. So our model apparently really describes the experiments which are known very well. These are very different materials. These are 14 different binary and ternary crystal structures of very different crystal structures. And we offered 17 properties, like vibrational properties. You will see some of them in the moment. This is offered, and what is the result? The result is a function. Now we plot this as a logarithm because kappa goes over 4 orders of magnitude, and just to make it easier to show, you show the logarithm of this quantity. So the logarithm of the predicted thermal conductivity is a constant plus another constant plus descriptor d1 plus another constant plus descriptor d2. And here are the functions which CISO determines. It's a function where we have the average mass of the atoms plus some constant, which is also determined by CISO, the reduced mass, the biofrequency tells you about the vibrational spectrum at 0 temperature, and you see, in fact, another phonon frequency. And very important, you find one parameter, sigma A, is a parameter which measures the degree of anharmonicity. And this is this material map which goes together with this. So this is D1 and D2, like our cloud picture, right? D1 and D2. And the color code tells us the predicted thermal conductivity. So we have very good thermal conductivity in the dark region and very bad thermal conductivity in the white region. The data points which we have used for the training are the ones which you see here. But we don't have really data points here, we don't have data points here, and we don't have data point here, but we have a prediction for that. The region of interest is this upper region. So we're looking for materials in this region, but there's nothing there yet. But CISO tells us you should look for systems which have a D1 and a D2 value, which corresponds to this. Now these are from the 17 offered genes. The system tells us 7 are important. So we use these 7, but in fact we looked a bit more carefully and found that not all 7 have the same influence. There are some in the sensitivity analysis, there are some which have a bigger effect than others. So at the end there are 3 which are particularly important. It's the molar volume, basically the volume of the unit cell, it's the frequency, the Debye frequency, and it's a large anharmonicity. So the larger the anharmonicity, the better is the insulation of thermal heat, of heat. So we now can, in fact, look at materials which fulfill this condition. So we just screen without really doing big calculations. We screen over materials which we obtain from which are given in the materials project, where we know the parameters, but the thermal conductivity is not known. Of course, you can say we calculate the thermal conductivity, but this is possible nowadays with the method we have developed, but it's extremely expensive because thermal conductivity of anharmonic systems requires some very long correlation function evaluations. But having these systems, we find 16 materials, which you see here, which are in this region of interest. So in a very fast way, we screen over these systems with these materials from the materials project database, and we find 16 of them have a thermal conductivity which is very, very low. And then we can look at it. Now, these are predictions, right? And I said machine learning gives you a prediction, but in principle also gives you a variance, an uncertainty. Now, so far, up to, say, some months ago, we did not really have an uncertainty in CISO. So what we did then, we looked at several of these data points to be sure that this is really a reliable prediction, and here we found it. Now, with two other postdocs, we are looking more carefully in uncertainty. So we also create an ensemble of CISO models. Different CISO models which have the same description for the known data set, but a different description for the out of the domain data. And with this, we also have, in fact, uncertainties. And we can do this in the same way as I did it before in the Gaussian process example. We can make predictions of, for example, these points. We add only these points which have a high uncertainty, and we continue and making a better CISO model. So with this, I'm sorry that I'm overrun 10 minutes. I'm really at my last slide as a summary and outlook. I think in material science, but you can use maybe similar methods also in other fields. There is a big chance, but also still a very big challenge for finding better materials. We think creating maps of materials is the way to go. Not just really calculating more and more individual data, but having really a map that you can really get an idea. In this region, I should really look more carefully. And I showed you, for example, this example here for thermal insulators, where we identified the region where we want to be, and we in fact found 16 examples which seem to be very good in thermal conductivity, but have not been considered so far. The methods where I see, or the methods which we at least use at the moment and which I think are most promising, are for sure neural networks, but also symbolic regression. The advantage of symbolic regression is that the parameters which enter, they have some physical meaning. So you get at least some insight what could be actually the reason for the correlation which you find. We think it's very important for our field, but I think in fact particularly also for other fields, to have an active or sequential learning process. So not just collecting data randomly, because then you will have a lot of redundant data, and your machine learning model may be actually getting very good in this region, but maybe this is the region which you're not interested in. Redundant data also put the wrong emphasis on some regions. So active learning gives you more information. We should look for data sets which have information, not just big, but information. We also, other people, I would say, are looking more into large language models, which look promising, but also really have, as you may know, actually a lot of problems, but still there is a lot of interesting challenges. I see a lot of open problems, so I think science is still urgently needed, and science means material science, but also mathematics and computer science. Anything which is out of distribution. You see, in this case here, the distribution where we have data is here, and we don't really know about the reliability of anything which is a little bit outside of this distribution. We need actually a better understanding how reliable are out of distribution predictions, and that means we need better theory, better concepts for uncertainty quantification. We have one way of what we call a domain of applicability. You know that every theory has a domain where the theory is good, and if you are outside, you need a different theory. And the same is true, in fact, for a machine learning model. There is a domain where this model which you have is good, and outside you should be careful. We have some mathematics which describes where that is. It's a little bit too complicated to be practical, but having really ideas, where can you trust your prediction and where not, is really important. And the quality is important, the amount of data is important, but with quality also, I mean really information content and much more. And with this, I just really want to say we have a fantastic program in Europe, this so-called European Research Council, which is for young people, starting grant, or for somewhat advanced consolidator grant, and for people like me, a senior scientist grant. which gives you a lot of money and you can really do basic science with this. Very often in our field, science comes together with some other boundaries, which I think are not good, because when you do good science, you never know exactly for what it's good, right? I mean, other people will use it in the good, but actually also in the bad way, unfortunately. But I think actually having fundamental science, which is not application driven, is also very important, and ERC is helping on this. And again, thank you very much for your attention.
Thank you, Matthias. Always impressed.
Thank you, Matthias Scheffler, for presenting. So I have two questions. The first one is about the nomadic. So it is a very big internet, and so I assume there are like working on it. So people use different business sets, different functional or even small potentials. So how can we? Is there already a way to unify all these different settings and use them for like a single AI model, or we have to only use the same setting for a single AI model?
Yeah, it's a very good point. It's somewhat a point which motivated me when we started that work, that we wanted to have data from all the different computer codes. Now, there have been tests that if you are very careful, the pseudo-potential codes, and we are doing all electron calculations, for good basis sets really at the end give the same results. But you have to be really very careful, and different pseudo-potentials also give different results. And we are working on it. We have, in fact, some ideas and some first publications, but nothing really complete, which tells you that even if this calculation is done with a basis set which is not good enough, that you can actually predict what would be actually the finally converged result. But at the moment, we are not yet there. This is what would be really great, that you could do this for different. At the moment, I would stay with one computer code. Yeah, but it's not really what I would like to say, but this is the way it is.
The seasonal method you choose is very elegant and have very insightful consideration of this interpretable descriptors. But so in recent 1 year or two, we are seeing a kind of different trend. So we have these large language models, and people are just kind of using brute force in more data and bigger model. And I think the material discovery the community is kind of following this trend. Just use more data and more larger models. So, do you have any comments on this
Let's put it this way. I think actually it's very interesting, and I'm following it. The problem, which you also indicated by your question, is that in the large language models, which look very promising, you need an enormous number of data. I mean, you see, we will never have as much data as ChatGPT has used to train. And if you ask ChatGPT a very specific question where you know the answer, it's very often the answer is not correct. So even in these most advanced systems, you don't know actually how the truth is. And I think actually when I said today, right, also in the methods which we are using, we want uncertainties. I really think also ChatGPT should tell us about uncertainties of their prediction. So yes, there are really models in polymer science, in different type of science where they believe they are on the way and they're still testing it. I'm following it. At the moment, I'm not really convinced that we will have enough data for doing this. Also, a little bit because I feel that a lot of data which we have is really redundant, and you need more information. You not only need more data, you do need more information to really train it properly. So I would not really stop someone to do large language models, but I would not do it myself.
So for the data in this paper, are they for pure crystal, or you already included the doping effect into account?
These are for pure crystals. Because the problem is really if as soon as you go to doping things in these systems, the concentration is not so well determined. It's getting actually, it's really because these are experimental data. So it's getting really very messy and having that you really know what has been measured. Yeah. But yes, I mean, at some point, if you have more data, then you could do this. And you could also have some error in the data quality. But with so few data, there's no way.
So,
yes,
Thank you for the wonderful talk. So here we are talking about you predict some static property of material, right? So in a larger problem, even larger problem is that you have time-dependent process. For example, dynamics. Let's give you an example. For example, shining a laser on the material, which cause even nonlinear dynamics. In this case, you have to solve the TDFT, and even coupled with the Maxwell equations. So I want to hear your suggestion or ideas how AI or ML can help with the dynamic problems. Yeah.
Yeah, I think I have probably two answers to that. The first thing is, if you talk about a material's property, I mean, say thermal conductivity, if you look when you really calculate this directly, you have to calculate it by including the full dynamics, including all non-linear effects. And if you go to electrical conductivity, which we also now actually are doing, where you also need the energy states, you also really need to know about, say, lifetimes of excited states and so on. At the end, in the things which matter for most of the performance of materials, you have a time average over them. So in material science, in the sense of talking about materials properties, the question is somewhat averaged away because you look at the statistical average. Now, of course, in terms of basic science and in terms of the science, which I think Angel Rubio will discuss, is it tomorrow? When is Rubio is talking?
Monday, yes.
So if you really look into just scientific properties and how really electronic systems behave under a laser field, what you mentioned, then of course you would need to include, then you would actually have a different type of question. But I would not see a reason that you could not also use machine learning for that if you have enough data. Again, I mean, if you see what they are doing, they work very, very hard to have actually one system characterized very well, right? Now, if you have 100 systems, then you could maybe actually predict the next 100, right? And then it would actually make a lot of sense. At the moment, I would not really necessarily see that these methods would help. Now, in the dynamics, actually, they could help. When you look at the coupling of electrons and nuclei, this machine learning interatomic potentials, if you really design it a little bit even further, and including electronic excitation, that could make actually also such processes easier to handle. But with all the dangers that you don't know how reliable that is.
Thank you.
So we also have like 4,800 audience online. And,
Thank you.
But I didn't see the question there. Yeah. Question? Oh, yeah.
Thank you for your talk today. I'm a student doing the experimental research. So my question is about the experiment. As you know, the experiment cost is very expensive, much more expensive than the DFT or than the machine learning. But we use computational or machine learning approach to do the prediction. Finally, we have to experimental verify that. But nowadays, we see a lot of emerging papers on verifying the computational or the machine learning predicted materials. So what's your suggestions on the experimental verifying of the predicted materials?
Yep. I mean, just a little bit of a comment of your first statement that experiment is so much more expensive than the theory. If you really calculate the thermal conductivity, we are getting very close to the expensive of experiments. But in principle, in fact, this example here these are experimental data, right? So the training was with experimental data. For this, okay. This was from your pen, right? The training here, the training data were all experimental, and then we used just the theoretical the materials project data to make these predictions. So at the end, I definitely agree with, you didn't say this explicitly, but it was implicitly in your question. At the end, the proof or the confirmation has to come from experiment. So what we would also say is, if you have these experimental data, there's no need to add more. If you then actually would say, there's another experiment which would add a point here. I said, forget it. This does not add more information. You should add information. So it helps experiment to identify which next material you should study. Right? In that sense, I think this machine learning would work for theory and for experiment. And we have, in fact, a nice collaboration with the people in Catalysis in Berlin, Annette Trunschke, which also goes with perovskites, where we told actually this is a good candidate for the next perovskite. And then she was sitting down and doing the crystallization, which takes half a year, one has to say. It's really a big thing to really create a new crystal. But that was actually also an interaction that you make a prediction, you tell the experimentalist, this is the good material, just try this. And then so also in an iterative way. So you can use it the same way as we are using it here, right?
Okay, thank you.
Yeah, two small questions. One is about this active or sequential learning. You need to define its acquisition function, or evaluate that function. And is that easy to calculate that function?
Yes,
or easy to obtain?
Yeah. So I discussed two acquisition functions, and so far we are still using these two because there are not so many good ideas yet to do better. Because there's not so much information. So one acquisition function, say, this is my predicted mean value, and I just go there where the mean value is where I want to be. And then you add this to the pool. But that may be not really giving you so much more information. And the other thing would be really just having an acquisition function, which is a type of addition. You have the mean value and the variance. And if the variance is in the region, again, covering the point which you're interested in, then you say this is a good point. But it depends really on the question of how reliable is this variance, right? How reliable is the uncertainty? So I think if you have an uncertainty, creating an acquisition function is very easy, and it's just some maybe also subjective addition of these two quantities, mean value and variance. But the question, I think, is really finding better ways of having uncertainties. I mean, we have found some situations where the uncertainty was very, very small, but the error was huge. This is the problem. You learn from the region where you have data, and you learn also the uncertainty from this region. And even if you're far away, it could give you actually a wrong impression. And I think there are more than 100 papers in this mathematical type of developments to really discuss how to get to better uncertainties. I've not found the solution yet. So I think it's a very challenging, important question to really look into this more carefully.
Another small question. So on one slide, you showed these two machine learning methods, random forest and Gaussian process, with two procedures, right? One is an improve the expectation of pure exploration, right?
Yeah.
Kind of for flavors. Somehow with this random forest, seems with this improved expectation, the performance somehow even gets worse from the plot, right? This looks, why is that so?
We have not fully understood that. So we have what happens in some of these cases. I mean, you have your uncertainty, or you have your acquisition function, and it seems that in fact sometimes you can be caught in some local minimum, and the system does not get out of it, and then you don't improve very much. So it's really, and that's why it's really so important to, unfortunately, look at more models to really avoid that, because if you don't know the potential energy surface, I mean, it will be never as smooth as the one I showed you, right? I mean, there will be many more minima. So you have, as we also have it in DFT, you can always be caught in some local minimum. And if you don't help it, it will not really get out of that. And in principle, it looked to be a random forest problem, but I think this can happen also with Gaussian process, right? It can always happen.
Talk. I have two questions related to machine learning talk potential. The first one is that in most of the periodic boundary condition system, we tend to use the PBE level of density functional theory calculation. Is there any much improvement if we can substitute our data set to a more higher level of DFT calculation level?
Yeah. There are two answers to that. The first answer is, for many questions, PBE may be good, but in fact, we also know for many questions, PBE is not good enough. And we are definitely, when we do density function theory in my group, we have done a lot of development that we now go to hybrid functionals. That's one thing where you are better, but still you're not really perfect, right? I mean, all these better functionals are more flexible. They're not always better. Now, hybrids have more physics because they have this exact exchange and they are better. Now, but there is also machine learning ideas, and Igor Zhang from Fudan University has, for example, a method where he starts from some hybrid functional and adds a machine-learned correction to this. This looks very promising and very good. I think so far it was only for molecules, right? We heard this morning. I think this would be really, I think, an approach that you really say, we start with a standard functional and we try to do the improvement by a machine learning correction. But of course, you need first data to really learn this correction.
Okay. And the last question is that besides of active learning with uncertainty analysis, there is another model deploying methodology like the pre-training of large atomic model and fine-tuning methods. Do you think? Do you have any opinion about this new training methodology?
I mean, this goes also a little bit to what people call the fundamental models and things, right? I think actually intellectually they are very interesting. I've not really seen, and I think actually we will also go in this direction, I should say that. So we will go in this direction. But if they really have more realism than hope or hype, I'm not sure yet.
Okay, thanks.
Okay. For all the students who have asked the questions, you have a small present you can take from here. Okay. So the last thing we do is that we have some present for Matthias. Liang You, can you come? Maybe I think it's better for you to represent the school, right? And It's our school.
You school?
Yeah.
I think you are here. Give a talk.
Yeah. So we entered.
We entered here.
We entered from here.
Yes.
All right.
Yes,
Okay.
yes.
Okay.
Thank you very much.
That's a nice idea.
Yes.
Okay. Okay. Yes. Thank you very much. Thank you.
So I think we can finish. And thank you again. Yeah, thank you for coming and giving the questions. Okay, cheers. Bye.
Thank you very much.